We are going to learn about a new method of integration known as integration by parts. Every differentiation rule has a corresponding integration rule. For example, we know that derivative of sine x is cosine x, which means that the integral of cosine x would be sine x. Similarly, the derivative of natural log of x is 1 over x, so the integral of 1 over x would be natural log of x. We have chain rule in differentiation. Its corresponding integration rule is u substitution, which we already have learned. Now there is a product rule in differentiation. Its corresponding integration rule is integration by parts, which is what we are going to learn today. Before I start the derivation for the formula of integration by parts, let's review a little bit about differentials. If I have a function f of x, its differential is given by f prime d of x. We will keep this in mind when doing the derivation. Integration by parts is used when we have to integrate a product of two functions. The two functions that we will choose to represent symbolically would be u of x, a function of x, and another function v of x. Do not mix this function u with the u of u substitution. So integration by parts will help us figure out the integral of something that looks like this. The product of u and v, and we have to integrate it. So let's consider this product of u and v and differentiate it. We know the product rule of differentiation, so this would be u v prime plus v u prime. Let's integrate both sides. So when we integrate, the left hand side just leaves us with the product, and the right hand side is u v prime plus v u prime whole integral. Because of addition property of integration, we can split it into two integrals, u v prime dx plus integral of v u prime dx. Now remember, I said that we will use differentials. So if a function f is given, its differential is f prime dx. Do we see a differential here? Yes. V prime dx is actually the differential dv, and u prime dx is the differential du. So we can rewrite it in compact form like u dv plus integral of v du. And on the left hand side, we have the product uv. Let's rearrange it a little bit. I'm going to isolate this integral u dv. So this is our final formula for integration by parts. What does it mean? It's saying that if we are taking this integral of u with respect to v, that is equal to the product of the functions uv, and we have moved the integration from with respect to v to taking the integration with respect to u. Why would this be useful? Because the actual integral that we are starting with would be difficult, and if we switch the integration from with respect to v to with respect to u, this second integral would be easier to solve. It will make more sense as we look at some examples. Let's solve some examples. I have kept this formula for integration by parts here for reference. We have to integrate product of x and sine x. Let's see how does it compare with the general formula of integral of u dv. Let us choose that x here is u and sine x dx is dv. How will you know which part of the integral to choose as u and which part as dv? You will learn it by practice and experience, and I will provide you a general strategy of looking at the integral and choosing u and dv. On the side here, I will keep track of what I have chosen as u and what I have chosen as dv. So u is x and dv is sine x dx. In the formula, we need v, which means we need to integrate it and obtain v from here. And we also need du, which means we need the differential of u from here. So u is x, its differential would be dx. Differential dv is sine x dx, which means that the function itself v we can obtain by integrating is minus cosine x. Now we have all these four parts. We can go back and put it in the formula here. So the integral of x sine x dx is the product uv. U is x, v is minus cosine x. So product x minus cosine x minus the integral v du. V is minus cosine x and du is dx. Let's simplify it. So this is minus x cosine x plus just the integral of cosine x. What's the integral of cosine x? We already know it is sine x plus c for the definite integral. Notice here we started with a difficult integral, and right now when we move the integral from with respect to v to with respect to u, we obtain a second integral which was easy to solve. Also notice about the choice of u and v. I have chosen u so that when you take its derivative or differential, it becomes more simpler. And I have chosen dv so that we know its integral. This is the general strategy of using u and dv. Let's try if I switch. If I choose sine x as u and x dx as dv. So same problem, same integral, just written a little bit differently. Integral of x sine x dx is written as integral of sine x x dx. So let's choose sine x as u this time and choose x dx as dv. So u is sine x, du would be cosine x dx. dv is x dx, which means the function v would be by integrating x square over 2. Let's put all this in the formula now. The product u times v, so sine x times x square over 2 minus the integral v du. V is x square over 2 and du is cosine x dx. We started with a function that had product of x and a trig function. Now we have to do an integral that contains product of x square and another trig function. So in fact, we have made the integral more complicated. And if we continue choosing u and v in the similar pattern, we will keep on making the integral more complicated. So this choice of u and dv is not useful. Again, the general strategy is choose u so that when you differentiate it, it becomes simpler, and choose dv so that you know its integral. Here we have chosen dv and we could integrate it, but we chose u so that its differential did not become simpler. That's why this overall integration is not working.